Hey everyone, and welcome. Today, we're going to dive into a super powerful tool in your trigonometry toolkit. Think of it like this. We're going on an angle hunt, and our weapon of choice is the law of cosines.
So picture this. You're handed a triangle puzzle. You know the length of all three sides. You know, the classic side, 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 or SSS case. But you don't know a single angle. So where do you even start? How do you crack that first angle?
Now, I know what you're thinking. Hey, I'll just use the law of sines. But here's the catch. The law of sines is amazing, but it needs an angle and its opposite side to even get started. If you've just got three sides, well, you're kind of stuck. It can't help you. We need a different tool for the job. And this is where our hero comes in, the law of cosines. And specifically, we're going to need a special version of it, one that's been rearranged specifically to hunt for those missing angles. And here it is. You might recognize the standard law of cosines, but this version has been tweaked to solve directly for the cosine of an angle. Now pay close attention here. See how side C is the one being subtracted up top? That's because it's the side opposite the angle we're looking for. That little detail is the absolute key. So why is this so great? Well, think about when you use inverse sine. It can get kind of tricky, right? You might get an acute angle when the real answer is actually obtuse. It can be ambiguous. But inverse cosine, no way. It gives you one unique, correct angle between 0 and 180 degrees every single time. If the cosine value comes out negative, it tells you, hey, this angle is obtuse. No second guessing, no extra checks. It just works. Okay, enough talk. Let's get our hands dirty and see this formula in action with a nice, straightforward example. All right, so here's our setup. We've got a triangle with sides measuring 6, 8, and 10. Our mission, should we choose to accept it, is to find angle C. That's the one across from the longest side, the side with length 10. So let's plug our numbers right into that formula. We've got 6 squared plus 8 squared minus 10 squared, all of that divided by 2 times 6 times 8. And check this out. The numerator simplifies beautifully. 36 plus 64 is 100, and 100 minus 100 is, of course, 0. So the cosine of our angle C is 0. And what angle has a cosine of 0? Yep. Exactly 90 degrees. This means we actually have a right triangle. It's kind of cool, right? When the angle is 90 degrees, the law of cosines basically turns into the Pythagorean theorem. And hey, if you look closely, you might notice this is just a classic 3, 4, 5 right triangle, but with every side doubled. Okay, that was a nice, clean one. But what happens when the triangle isn't quite so perfect? Let's take on a tougher case. One with an obtuse angle. All right, new triangle, new challenge. This one has sides 4, 7, and 10. And this time, let's go for the whole shebang. We're going to find all three angles and see this process through from start to finish. Now, before you start mashing numbers into your calculator, listen up. Here's a pro tip that is going to save you a ton of headaches. Always find the largest angle first. And how do you know which one that is? Simple. It's always the one opposite the longest side. Okay, let's follow our own advice. Side C is our longest side at 10, so we'll find angle C first. We plug in the numbers, and we get a cosine value of negative 0.625. And remember what a negative cosine means. Boom, we've got an obtuse angle! Your calculator will tell you it's about 128.7 degrees. Now here's the cool part. Since we found the biggest, trickiest angle first, we know the other two have to be acute. So now we can safely switch to the simpler law of sines to find angle A, which is about 18.2 degrees. And for the last one, angle B, we just subtract the other two from 180, which gives us 33.1 degrees. See how smooth that was? All right, for our last example, let's look at a case that seems totally normal on the surface, but, well, it's hiding a pretty big secret. So here are our sides, 2, 3, and 10. Seems simple enough, right? Let's follow the same process. We'll try to find angle C, the one opposite the longest side. We plug everything into our trusty formula, run the calculation, and we get that the cosine of C is, wait, negative 7.25? If you've been paying attention, that number should be setting off all kinds of alarm bells in your head right now. So why is that so alarming? Because the cosine of any angle has to live somewhere between -1 and +1. It's a hard rule. A value like negative 7.25 is way out of bounds. The math here is literally screaming at us, telling us something important. This triangle is impossible. It cannot exist. And this all circles back to a super fundamental rule of geometry, the triangle inequality theorem. All it says is that if you add up any two sides of a triangle, the sum has to be bigger than the third side. In our case, 2 plus 3 is 5, and 5 is definitely not greater than 10. Those two short sides aren't even long enough to meet. The law of cosines didn't just give us an error, it actually proved this for us mathematically. How cool is that?
So we've seen how powerful this formula is. It can find any angle, and it can even prove when a triangle can't exist. Now, to make sure you can use it correctly every single time, let's go over the single biggest mistake people make.
Here it is, the most important detail to get right. That little minus sign in the numerator, it is everything. Always, and I mean always, make sure you are subtracting the square of the side that is directly opposite the angle you are trying to find. If you're looking for angle A, you subtract A squared. Find an angle B, subtract B squared. Get that one thing right and you'll be golden.
So you might be thinking, okay, this is neat for a math class, but where in the real world would I ever use this? Well, the answer is actually all around us. Let's talk about robotics for a second.
Just picture a robotic arm on an assembly line, right? You've got the shoulder joint, the elbow joint, and the hand at the end. Hey, that forms a triangle. The lengths of the arm segments don't change. Those are your sides. Now, to get that hand to a precise target, the robot's brain needs to figure out the exact angles for the shoulder and elbow. And how does it do that? You guessed it. It uses the law of cosines to solve that triangle and find the perfect angles for incredibly precise movements. So there you have it. The law of cosines is so much more than just a formula. It's a key. It's the key that unlocks the side-side-side puzzle with total precision and zero ambiguity. So the next time you see a triangle, just remember, you've got the tool to uncover all of its secrets. Thanks for joining me.